previous lecture, we derived and solved governing differential equation of plate buckling by using equilibrium approach, which was based on small deflection theory. Now, we will take same example for finding critical load by using energy method. The example problem was simply supported plate uniformly compressed in one direction. Let us start. This is the problem we will have to solve, and we will have to use the energy method. This is the definition of the problem which we are going to do, that is critical load by using energy method for simply supported plate uniformly compressed in one direction. This is the same problem what we solved. This is for thin plate. In our assumptions, we have considered it is thin plate. So, it is thin plate, and because of this thin plate, this sigma z value, stress in the z direction, we had neglected it, and gamma xz is equal to gamma yz is equal to 0, negligible. Then the strain energy of the plate due to bending, that we can write as U is equal to, this is half stress into strain. The stress, available stress are sigma x, sigma y and tau xy. So, the strain energy is half. We will have to integrate the complete volume. This is sigma x into epsilon x plus tau xy and gamma xy. So, we will have to integrate total complete volume. This is the strain energy due to bending. Now, we know the expression of strain. It is, we had just derived in the previous lecture, minus z into del square w by del x square, and epsilon y is equal to minus z into del square w by del y square, and gamma xy is equal to minus 2z into del square w by del x into del y. And we got the strain in terms of displacement. Also, we had derived the stress in terms of displacement also. Let me write that. Sigma x was minus Ez divided by 1 minus mu square to del square w by del x square plus mu into del square w by del y square. This was sigma x, and sigma y, let me write down, minus Ez divided by 1 minus mu square into del square w by del y square plus mu into del square w by del x square. This x y is interchanged here, just observation, and tau xy is minus Ez divided by 1 plus mu multiplied by del square w by del x into del y. And if we substitute this in the strain energy expression and if we integrate, we will find the strain energy in terms of displacement component. That is our objective, to find it out. So, you can write here as half, and it is integrated in complete volume of the plate. So, let me write the plate dimension 0 to A, again dimension 0 to B, and thickness is minus h by 2 to h by 2, and you can write sigma x into epsilon x plus sigma y into epsilon y plus tau xy into gamma xy. This is the thing, and it will be integrate dx into dy into dz. So, if we substitute this value, now you substitute sigma x, sigma y, tau xy epsilon x, epsilon y and gamma xy. If you do this, I am not going to do detail, but it is very simple. You will find u is equal to, I am directly writing E by 2 into 1 minus mu square whole square into minus h by 2 to h by 2 z square and integration 0 to a into 0 to b, it is 1 minus mu square into del square w by del x square whole square plus del square w by del y square whole square plus 2 mu into del square w by del x square multiplied by del square w by del y square plus 2 into 1 minus mu and del square w by del x into del y, this complete whole square, and this is multiplied by dx, dy and dz. This is the thing. And if we integrate, so I wish to mention here, you see this z square where you got, do you know, this is if sigma x 1 z is there and in epsilon x there is 1 z. So when it is multiplied, that becomes, that has come z square, and here at the denominator it is 1 minus mu square. To make it in standard format, we made it 1 minus mu square whole square, means we multiplied additional 1 minus mu square at the denominator, and here it is again, it is multiplied, and we divided with 1 minus mu square and multiplied with 1 minus mu square. So finally this will be the expression. You can do this as a homework. This is all right. Then if we will further simplify, implies this u is equal to d by 2. So d is equal to the bending stiffness of the plate, that is EHQ by 12 into 1 minus mu square, if you will write it, and this integration 0 to a and 0 to b. This one you can write it as del square w by del x square whole square plus del square w by del y square whole square plus 2 mu into del square w by del x square into del square w by del y square plus 2 into 1 minus mu into del square w by del x into del y whole square, and this is altogether dx into dy. So this is the strain energy, expression of the strain energy. Then same boundary condition what we had derived, I am writing here. The plate is simply supported. The plate is simply supported, hence the boundary conditions are that we had derived it, del square w by del x square is equal to 0 at x is equal to 0 and a, and del square w by del y square, this is equal to 0 at y is equal to 0 and b. So this is the boundary condition we had derived earlier. Now what you can do, you will have to assume a deflection surface can be represented by double trigonometric series. So we can assume as w is equal to the deflection surface can be represented by double trigonometric series that is this W we can assume as m is equal to 1 to infinite, n is equal to 1 to infinite, amn sin m pi x by a multiplied by sin n pi y by b. This earlier we had assumed the same thing, and we will have to substitute this assumed deflection in the energy expression, because energy expression is only the displacement W, then we can substitute this expression in the energy expression and we can find, we will have to integrate in fact 0 to a 0 to b, then you will get u is equal to, right here substituting W in the expression of strain energy, you will get, I am directly writing, you can do this exercise, AB is equal to AB by 8 into D into summation of m is equal to 1 to infinite, summation of n is equal to 1 to infinite, amn square, and it is m square pi square by s square plus n square pi square by b square whole square. So, this will be getting. Then this is the strain energy stored in the plate, and for finding the total potential energy of this plate, you will have to find the work done by the compressive force during buckling of the plate. This is stored as potential energy. So, you write the work done by the compressive force during buckling of plate is stored as potential energy V. We can refer this figure to find the total potential energy. Here I have taken a small thickness dy of the plate and which is acted by Nx, and in this case you can calculate dV, I am writing minus because work done is negative. This Nx is for unit length and this length we consider dy. So, because of that this Nx multiplied by dy is the force, and that force has gone the shortening, how much the shortening has been done because of the application of the load. This shortening is, the expression is, you may be remembering, that is 0 to L half into del W by del X whole square into dx. So, this is the external work done for this small element of thickness dy and length of complete length. We are integrating from 0 to, here not 0 to L, this is the span is A, so 0 to A, yes. And if you integrate the complete work done because of this external load, this V is equal to minus this Nx by 2 integrating 0 to A and 0 to B, this is del W by del X whole square into dx into dy, and if you integrate it, that will come minus pi square, because we know this W is the assumed displacement, this is the assumed displacement. If we substitute in the work done expression, that will come pi square b divided by 8a into Nx and summation of m is equal to 1 to infinite, summation of n is equal to 1 to infinite, that is m square amn square. This is the expression we will get for the external work done. So, the total potential energy is equal to U plus V, and critical load is obtained by minimizing the total potential energy. So, the critical load is the value at which the potential energy has stationary value. If we differentiate d of u plus v by dAmn, because this Amn is the unknown in the expression of the total potential energy, because of that we are differentiating with respect to Amn, this equal to 0. If we will do it, we will get the expression, this Nx is pi square a square into d divided by m square and multiplied by m square by s square plus n square by b square whole square. If you remember, we got also the same expression. This is the same expression derived by using equilibrium approach. This is the same expression derived by using equilibrium approach. Thank you.